In this video, we're going to talk about linear equations in two variables. For constants a, b, and c, we say that a linear equation in two variables is one of the form ax plus by equals c. The only rule or restriction on a and b is that they cannot be zero at the same time. I can have one being zero, but then the other has to be non-zero, and vice versa. So in this set of examples, we're going to determine which of the following equations are linear and which aren't. The first equation is 3x minus the quantity 2 minus 4y equals to x minus y plus 1. To figure out if it's linear, let's simplify it and try to convert it into standard form. This means that I need to simplify the left and right hand sides as much as possible, bring all variable terms to the left hand side and all constants to the right hand side. When I do all this, I'm going to end with the equation 2x plus 5y equals to 1. That means that this is linear. The reason I have to go through and check all this is to make sure that both my x and y variables don't fully cancel out, because at least one of the coefficients of x or y needs to be non-zero. In the next example, consider x plus 2 over 3 minus y equals to y divided by 5. The first thing I'm going to do is multiply by the least common multiple of all denominators. In our case, that's the number 15. When I multiply both sides by 15, simplify and move everything to the left-hand side that needs to be moved to put it into standard form, I'll get the equation 5x minus 18y equals to negative 10. So the second example is a linear equation in two variables. Next, consider the equation 4x cubed minus 2y is equal to 5x. Let me move all variable terms to the left-hand side, and then we'll see that I have a surviving x cubed term. In other words, I have a nonlinear term, which disqualifies this third example from being a linear equation in two variables. For a fourth example, look at x squared minus the quantity x minus 3 squared equals to 3y. Now, just because I see terms like x squared present, it doesn't automatically disqualify this. I have to simplify and see if anything maybe cancels out. When I FOIL that square term and I simplify and combine all like terms and then write it in standard form, it looks like those x squareds actually canceled out. I end up with the equation 6x minus 3y equals to 9. So I do have a linear equation in this case. That's why it's always important that we simplify, convert to standard form, and check. And just a couple more very fast ones. Suppose I have 3x equals 3 and 2y equals 0. Even though I only have one variable at a time, I still have at least one coefficient of x or y that's non-zero, so these do qualify as linear equations in two variables by definition. Again, because I am allowed to make one of those coefficients equal to 0, as long as the other one isn't also 0. In the video for section 2.1, we graphed the equation 2x minus y was equal to 1, and we saw that we got a linear graph, or a graph that presents as a straight line. We also saw some examples with terms like x squared and y minus 1 squared, which would force curves in our graphs. So that's another reason that we're giving the word linear to equations that have variables to the first power, is that their graphs are always going to be straight lines and they will not present with curves. Also remember the way that we graphed this equation. We took our linear equation 2x minus y equals to 1 and we solved for y. Then we started plugging in a couple of x values to get some information on coordinates, and then we just played this game of connect the dots. In section 2.4, we'll discuss more about linear equation forms, but the whole idea is that we need something a little bit more efficient than XY charts, because in general, XY charts, even though they're conceptually simple, they're tedious and inefficient and can honestly take forever. So to work our way up to this, we're going to start graphing linear equations by figuring out where their x and y intercepts are. If we have a linear equation where both a and b are not equal to 0, then we definitely have an x and a y intercept. Finding the x-intercept is pretty simple. We know that this is going to cross the x-axis at some number with a y value of 0. So to find the x-intercept, take your equation, set y equal to 0, and then solve for x. To find the y-intercept, the concept is pretty much the same. The x-coordinate will be 0 and the y-coordinate will be some number. So to find a y-intercept, in your linear equation, set x equal to 0 and then solve for y. And once we have both of these points plotted, we can connect the dots and sketch our linear graph. So let's put this into practice. Consider the equation 2x minus 5y is equal to 10. To find the x-intercept, we set y equal to 0. This gives me 2x minus 5 times 0 equals to 10. which reduces to 2x equals to 10, and I can solve for x and get a solution of x equals to 5. Next, for the y-intercept, I plug in 0 for x. This gives me 2 times 0 minus 5y equals to 10, which reduces to minus 5y equals to 10, which reduces to y equals to negative 2. Therefore, I have an x-intercept of 5, 0 and a y-intercept of 0, negative 2. So I can sketch the graph of 2x minus 5y equals to 10 by just connecting those dots with a straight line, and we're done. We'll try the same thing with the equation 3x plus 2y equals to 5. Again, the process is identical. Find the x-intercept by plugging in 0 for y, find the y-intercept by plugging 0 in for x, and then solve for your corresponding variables. This situation will give me an x-intercept of 5/3, 0, and a y-intercept of 0, 5/2. Then all I need to do is connect the dots by drawing a straight line between these points, and I have my linear graph. In section 2.4, we're going to talk about more line forms so the actual coefficients of our linear equations are a bit more revealing. Recall that when we were doing circles, the numbers embedded into our standard equation told us something about the circle. We can actually perform a pretty similar exercise when it comes to linear equations. Depending on the linear equation though, we're not always guaranteed an x and a y intercept. In the next slide, we'll talk about what happens when I have a horizontal or vertical line. So, there are possibilities of this. Basically, if our equation reduces to y equals to some number with no x value, then I have a horizontal line at that y value. Likewise, if my linear equation reduces to x equals to some number without a y value, then I have a vertical line at that x value. So here we're going to graph 4 linear equations that are either horizontal or vertical lines. Y equals 2, x equals minus 3, x equals 0, and y equals negative 1. The first one, y equals 2, says that I have a horizontal line at the y value of 2. So let's sketch that out. The second one, x equals to negative 3, says I have a vertical line at the x value of negative 3. The third, of x equals 0, says that I have a vertical line at x equals 0, and this just so happens to overlap with the y-axis completely. And the fourth, at y equals to negative 1, says I have a horizontal line at the y value of minus 1. In the previous slide, I said that we are guaranteed both x and y intercepts so long as our coefficients of x and y were both non-zero. And even though these 4 examples in this slide do qualify as linear equations, the absence of one or the other variable doesn't guarantee us both an x and a y intercept. It looks like each one of our equations in the form of y equals to something, all of those have y-intercepts but not x-intercepts, unless they were to overlap with the x-axis. X equals to negative 3 won't have a y-intercept, but x equals to 0 overlaps with the y-axis everywhere, so the entire line is a y-intercept. But that's kind of a special case. Alright, well thank you so much for your attention. We'll see you in the section 2.4 video on line forms.